It's important to recognize that physical transformations, like a solid melting and becoming a liquid, or a liquid vaporizing and becoming a gas, have enthalpy changes associated with them. It costs energy to loosen the molecules in a solid and push it past its melting point and turn it into a liquid. In this class, at this point in time, though, we are generally going to be more interested in the enthalpies associated with chemical reactions, where bonds between atoms are actually changing partners, as opposed to just physical loosening of molecules and transition from one phase of matter to another phase of matter. So in this brief lecture, we want to talk to you about thermochemical equations and how we represent enthalpies associated with chemical changes. So a thermochemical equation is simply a balanced chemical equation that has an enthalpy change for the overall reaction associated with it. So remember that enthalpy change is just another term for heat flow against a constant pressure. So in general, when we talk about an enthalpy change associated with a chemical reaction, we're just saying this much heat is absorbed or released by the chemical reaction occurring. And to represent the enthalpy change associated with a chemical reaction, we write what's called a thermochemical equation, which is simply a balanced chemical equation, which in addition to representing balanced relationship between the reactants and the products, we also include an enthalpy change, delta H, to show how much heat is absorbed or released by that chemical reaction as we write it. So for instance, another chemical reaction that can be used to power an instant cold pack is the mixing of the solid ionic compound barium hydroxide octahydrate with ammonium chloride. If you mix 1 mole of barium hydroxide octahydrate with 2 moles of ammonium chloride, you will get a chemical reaction that produces barium chloride dissolved in water, 2 moles of ammonia dissolved in water, and 10 moles of water in the liquid phase. Please adjust that phase script for me. That's liquid water. And the enthalpy change of this reaction is endothermic, where 80.3 kilojoules of heat is absorbed by the reaction. So if we write the balanced chemical equation and we know the enthalpy change associated with mixing 1 mole of barium hydroxide octahydrate with 2 moles of ammonium chloride, we have a delta H, an enthalpy change for the overall reaction, and we refer to the balanced chemical equation with the amount of heat absorbed or released by the balanced chemical equation listed next to it as a thermochemical equation. Just as a reminder, the sign on delta H obeys the same conventions that the sign on Q does. So if your delta H is positive, then your reaction is endothermic. In this case, the reaction is endothermic and absorbs heat from the surroundings, so the reaction will be cool to the touch. And the enthalpy change is a positive 80.3 kilojoules per mole of barium hydroxide octahydrate that you mix with 2 moles of ammonium chloride. This reaction is in fact so endothermic that you can actually use it to freeze the reaction vessel that you're running the reaction in to a countertop or to a board. And I've actually included a video of that below the lecture materials today. If we're talking about thermite or very exothermic reaction, we can also represent that with a balanced thermochemical equation. And in many ways, this is just as useful because understanding how much heat is released by exothermic reaction is essential to predicting how good a chemical is going to be at a fuel source, as a fuel source. So if you're talking about the combustion of natural gases, we're talking about reactions that are potentially explosive and release a lot of heat. Knowing how much heat is released per mole of reactant is essential to gaining some control over that reaction and putting it towards a useful purpose. So if we look at the thermite reaction, the balanced chemical equation for the thermite reaction, once again, is 2 moles of solid aluminum react with 1 mole of solid iron 3 oxide to make 2 moles of solid iron and 1 mole of solid aluminum oxide. This reaction is exothermic, and the enthalpy change for the reaction, delta H, is negative 852 kilojoules. So when you have an enthalpy change next to a reaction, you're going to initially see it written as either delta H or delta H with a subscript RXN for reaction. We know the reaction is exothermic because there's a negative sign on the enthalpy change associated with the reaction. And what the thermochemical equation is saying is that for every 2 moles of aluminum that we run this reaction with, 2 moles of aluminum participating in the reaction would release 852 kilojoules of heat. So notice that the enthalpy changes are for the reaction as written, and you're only going to get that 852 kilojoules of heat released if you can run this reaction with starting with 2 moles of aluminum and 1 mole of iron oxide. It's also important to know that if you run the reverse of the reaction, the reverse of a chemical reaction must or absorb or release the same amount of heat as running the reaction in the forward direction. But if you reverse the reaction, the sign of the enthalpy changes. So if you run the thermite reaction, 2 moles of aluminum reacts with 1 mole of iron 3 oxide to make 2 moles of iron metal and 1 mole of aluminum oxide. This is exothermic to the tune of negative 852 kilojoules. If I try to run the reverse reaction, when I run the reverse reaction, 2 moles of solid iron reacts with 1 mole of aluminum oxide, giving us 2 moles of aluminum and 1 mole of iron 3 oxide. The enthalpy change is the same magnitude, but now it's positive. Now this reaction would be exothermic, and you would have to have 852 kilojoules of heat absorbed from the surrounding environment to successfully run the reverse of the thermite reaction. So this is true for any chemical reaction, and this is a function of enthalpy, being what we called before a state function. The amount of energy, including the heat energy, gained or lost by a chemical reaction is just a function of the chemicals and their physical state, the condition of the system where you started and the condition of the system where you finished. So it doesn't really matter how I go from here to here. If I start here and I end up here, the reaction releases 852 kilojoules. If I do the opposite, I start here and I end up here, the magnitude of the enthalpy change is the same, but the direction is different. Now the system has to absorb heat. So always remember, and this will be important in a little bit when we talk about Hess's law, because enthalpy is a state function, and it only depends, the enthalpy of the reaction only depends on whether you start at point A and end up at point B, or start at point B and end up at point A. If you run the reverse of a chemical reaction as written, you know the enthalpy change for that reaction. It's the same magnitude, but opposite sign.